Hello, my name is Abu Bakr Siddiq Iman, University of Frontier Technology Bangladesh, Department of Internet of Things and Robotics Engineering, ID number 2201011. Today, I am going to presenting my operating system and Unix programming lab course final project. The project title is Federated Learning Enable IoT-Based Real-Time Patient Health Monitoring System with Multimodal Analysis in RTOS. This project addresses the critical need for privacy preserving real-time patient monitoring by combining IoT sensor with advanced AI technique. In the background and motivation for this project, the healthcare landscape is changing dramatically with an aging population and increasing chronic disease, especially highlighted during the pandemic. IoT technology enables continuous, non-invasive home monitoring with early detection of abnormal condition, constructing sharpening with traditional hospital-based monitoring that is expensive, requires constant attention, and provide only snapshot rather than continuous data. Current IoT health monitoring system fall into two categories: agentic systems that are fast and private, but use simplified models with limited accuracy around 85 to 90%, and cloud-centric systems that achieve higher accuracy around 90 to 93%, but introduce high latency, privacy concern, and internet dependency. Neither approach alone provide the complete solution needed for real-world healthcare development. Through my literature review, we identify critical gaps. Most systems lag end-to-end integration. Privacy preservation is often an afterthought. Existing systems are unimodal, but my system is multimodal. Existing system using only vital signs. There's a significant research gap between laboratory and real-world accuracy, and most solutions lag interpretably, giving prediction without explanation that clinician cannot trust. My proposed system to address these gaps, we propose Health Monitor Federated Learning, a full-stack IoT system combining edge and cloud paradigms with key invention including federated learning for privacy, preserving model training, multimodal analysis combining vital sign and patient image, vision language model for interpretable description, and dual interface design for clinical workflows and demonstration. System architectures. My system has four main layers. The sensing layer at the patient beside features a Raspberry Pi with ESP8266 coprocessor connected to DHT11 AD8232 ECG sensor, MAX 30100 sensor, motion sensor, and Pi camera. The edge processing layer performs local training and never transmit raw patient data. The federated learning layer coordinates learning across multiple homes. The multimodal analysis layer uses Llama 3.2 vision language model for image analysis. And the visualization layer provides both web dashboard and desktop interface. In the hardware implementation, I use four types of biomedical sensors: for heart rate, for oxygen saturation, for temperature and humidity, and a motion sensor. In my sensor and my system manually send data for every 50-second latency, but when the patient is moving and the motion sensor detect the patient movement, then this priority is 1. And in that time, instead of 15-second latency, it take data in 5-second latency for emergency data collection. After the data sent to my local ESP8266, then a flower method for federated learning system model is updated by this data. In healthcare, data privacy is paramount. My federated learning pipeline works step by step. Each client collects 5 samples, train a PyTorch-based multi-layer perceptron locally for 5 epoch, extract only model parameters, send encrypted parameter to the central flower server, which applies federated averaging, and send the improved global model back. Throughout this process, raw patient data never leaves the edge device. The curated IoT health dataset from Kaggle include heart rate, oxygen saturation, temperatures, and derived features like heart rate variability. Features are standardized class imbalance addressed with smart atomic resampling and hyperparameters optimized by randomized search. On the health outtest set, the federated learning model achieves 99.8% accuracy. In multimodal analysis with BLM, every 15 seconds, the Pi camera captures an image trigger for analysis through n8n workflow. Llama 3.2 vision language model with 11 billion parameters analyze the image using a careful crafted prompt, generating natural language description like patient appear relaxed, sit upright with normal breathing, or patient is moved forward, breathe rapidly, showing sign of distress. This description appear alongside vital beside predictions, giving clinical explanation they can trust. Clinicians see live vital sign card with color icon based on threshold. Interactive trend chart showing historical pattern and a prominent predict health status button display result with confidence score and BLM description. The dashboard auto-refresh every 10 seconds. For local use, we built a custom Tinker desktop graphical user interface with live camera preview, manual capture button, and demo mode toggle. In the performance and result, the federated learning model achieved perceptions of 99.7% for low risk and 99.9% for high risk. Recall of 99.9% and 99.7% respectively. F1 score at 99.8% for both classes and AIUC ROC at 0.98. This significantly exceeds traditional ACE system at 80 to 85% and Cloud Ensemble system at 89 to 93%. In then prediction latency is 3.5 seconds, while within acceptable limits for clinical monitoring. Comparative analysis between others. Compared to existing approaches, my system uses vital plus images as input. Combines federated learning with Stack, N10 and Llama BLM. Uses hybrid ACE cloud architectures. Achieve 99.8% accuracy versus 93%. Provides strong privacy with raw data local. Include multimodal analysis and interpretability with BLM description and offer a practical balance of complexity and deployability. In my system include hybrid federated learning IoT architecture strategically combining ACE sensing, federated learning and cloud-based BLM analysis. Privacy preserving federated learning ensure raw patient data never leaves the ACE device. Novel integration of Llama 3.2 vision language model with IoT health monitoring. Dual interface design catering to different clinical workflows. Graceful degradation during network outage and complete open source implementation facilitating adoption. Current limitation includes sensor validation requiring verification against medical grade equipment, BLM latency of 10 to 15 seconds for image analysis, initial training using synthetic data needing real-world clinical validation, limited population diversity testing, FL scalability needing testing with 50 plus client, and regulatory approval not yet purpose for clinical deployment. So my future work is near-term goals include clinical validation, studies with hospitals, differential privacy integration, and ACE optimization, and ACE quantization. Medium-term goals include enhanced multimodal fusion, real-time video analysis, audio integration for cough analysis, and additional biomarkers. Long-term goals include explainable AI integration, regulatory compliance, pursuing FDA clearance and CA marking, and commercialization through healthcare provider partnerships. In conclusion, I identify critical gaps in existing IoT health monitoring system and propose Health Monitor FL integrating Raspberry Pi based RTOS sensing with federated learning, combining vital signs and patient images for multimodal analysis. Using Llama 3.2 BLM for interpretable description, we demonstrate 99.8% accuracy, 2.5-second latency, strong privacy guarantees, and positive clinical feedback. This work bridges the gap between experimental research and deployable healthcare system, providing a template for next-generation remote patient monitoring that is accurate, private, interpretable, and practical, ultimately saving lives while preserving patient privacy. Thank you.